So today we are going to introduce the attributed graph clustering using contrastive learning and Unrolled ADMM network. My name is Brian Lin and my advisor is Professor Carson Fang and I'm from National Yanmin Chiao Tung University. So the main idea of this project focused on unsupervised graph clustering, not node classification. So we are given an attributed graph, which is Cora in our experiment, and we will learn the node embedding by aggregating graph structure and node features using our graph sage, the graph encoder. So the learned embedding will be applied to the unrolling network to construct an affinity matrix which represents the similarity between nodes. And finally, spectral clustering is applied to the affinity matrix, and the clustering quality is evaluated by NNI and ARI, which is the clustering performance index. And this is the overall block diagram. Uh, we may look back at this block diagram after we have learned all the individual blocks. So let's look at the first block, the graph augmentation. So and the purpose of the graph augmentation is to generate two different graphs that has two perturbed views. So the model will learn the embedding that are robust to small changes in features and edges by using this kind of contrastive learning way. So we have our original graph and it has the node features matrix X and the adjacency matrix E. So the augmented view, we will have our SA, EA, SB, EB. So these four matrices are generating using random feature masking and random edge dropping. So we'll just, as the name says, it just randomly masks some features to 0 and randomly drops some edge. So, and the second part is our graph stage encoder. So this graph stage is used to transform known features and graph structures into node embedding, which is most suitable for clustering because they contain graph structure information. So the implementation, the first step is to do a neighbor sampling in order to reduce computational cost and avoid neighbor explosion. For example, if the first hop, the one hop neighbor is the number of one hop neighbor is 10, and the two hop number, the number of two hop neighbor is 10, then the total neighbor we need to account for is 10 times 10, which is 100. This is a large number, so we need to do a neighbor sampling to reduce our computational complexity. And the second step is to aggregate neighbor features according to the adjacency matrix. And the equation, the simple equation is looks like this. So Z is our embedding matrix. So and these pictures says about the general concepts of the graph sage. So we have our original network which has the node and the edge. So we will project the node features into the embedding space so that we can do the clustering more easily by using this Z matrix. So yeah, so let's move on to the next part. So this part is Unrolled ADMM network. So instead of using iterative algorithm, we use this kind of Unrolled network. So let's talk about the purpose first. So the purpose is to learn an affinity matrix W from node embeddings, and this matrix represents the self-expression relationship between nodes. So the input is the output of the graph stage, so it's Z, and the dimension is n by p sub EMB. So the n is the number of nodes, and the p EMB is the dimension of the embedding. And so each row vector is one node embedding, and the output is the W matrix, which is n by n. So the element of W represents the similarity between node I and node J, and it will be used as the inputs of the spectral clustering. So the main idea of the ADMM is, instead of running the iterative algorithm many times, we will unfold this algorithm as three. In this experiment, we use three ADM layers. So we will have some trainable, learnable parameters in this kind of unrolled network, and the number of them is less than the usual neural network. Yeah. So the input is Z, and after going through three ADN layers, we will get our output affinity matrix W, and it will satisfy the self-expression property. Z transpose is approximately equal to Z transpose times W, and we will explain why later. It is due to the loss, the self-expression loss we have defined in the later slides. So the advantage of this kind of method is, first thing is interpretability. So each layer has a clear physical meaning based on optimization steps. The second thing is efficiency. So it will converge faster than the traditional iterative solvers, because the model just learns the optimal parameters by itself. The third point is domain specific. So it naturally integrates the physical model of a problem. And the fourth point is compactness. So the number of the learnable parameters is less than the black box neural networks. So, and in conclusion, it incorporates the domain knowledge of model-based method with a powerful learning capability of data-driven methods. And finally, we've gone into this loss function. So we have three terms. The first term is self-expressive loss, and the second term is info NC loss, which is contrastive loss, and the second term is the global smoothness loss, which is at the next slide. So self-expressiveness loss is just mentioned before. And we will have this kind of formats. We try to reconstruct our node embedding by using this kind of format, Z transpose times W. So we can see this equation as the linear combination of different node embeddings. For example, if the embedding of node 1 can be reconstructed using node 2 and node 3, then we will say that maybe node 1, node 2, node 3 all belongs to the same clusters. This is the main idea. So yeah, so Z transpose times W means this is a linear combination of the columns of Z transpose. So columns of Z transpose is just the row of Z, and the row of Z, as mentioned earlier, the row of Z is just the node embedding. So we can use this kind of linear combination formats to understand the self-expressiveness loss. And the second term is info NC loss. So this loss pulls the same node from two augmented views closer and pushes different nodes apart. So this is just the main idea of the contrastive learnings. Yeah, we will group the nodes into positive pair and negative pair and try to pull the positive pair closer and push the negative pair away. So, and the smoothness loss is just looks like this. So it encourages connecting nodes in the graph to have similar embedding. Yeah. And finally, this is the evaluation part done by using spectral clustering. So we use this affinity matrix W to obtain the final node clusters. So we will convert this W into a symmetric affinity matrix because the spectral clustering needs this um, kind of symmetric matrix to construct our graph Laplacian. So the equation is this. And after we get this L matrix, we will compute the eigenvectors of it and use them as the columns of spectral embedding matrix U. And the format is just like this. The U is equal to the first column U1 and so on and so forth to UR. And we'll apply k-means on this matrix to get our final node clusters. And in this experiment, because the number of cases in Cora is 7, so we will set the number of clusters to 7. And the number of eigenvectors is searched from 2 to 20. Okay, so let's look at the results of our code. So the loss will go all the way down to 10, and the N9 AI will improve as our epoch increase. Yeah, just like this. Let's do a final recap. So the overall block diagram is this. So the original node feature matrix S and the adjacency matrix A will be augmented into two different views. So the first view is S1A1, and second view is S2A2, and both of these views will be fed into the graph stage to generate two different embeddings, and we will use these two embeddings to do the contrastive learning. As mentioned earlier, we will use these two Z1 and Z2 to calculate the info NCE loss. And finally, we will use the original node feature matrix and adjacency matrix to generate the original embedding and feed it into Unrolled network to get our W, and use W to do the spectral clustering to get our final node clusters results. And here is the detail block diagram of our graph stage. So we will feed X and A matches into this graph stage encoder, and we have two hidden layers in our experiment. So after the first layer, we will generate Y, and Y will be input into the second hidden layer to generate Z. So in this part, we will do the neighbor sampling and the aggregation of the neighbor information just mentioned earlier in the slides. So this is the big picture of this experiment, and that concludes my presentation, and thank you for your time and listening. And this is today's presentation. Thank you.